Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. MLOps, short for Machine Learning Operations, is the discipline that combines the automation and reliability practices of DevOps with the unique demands of machine learning systems. It encompasses the end-to-end lifecycle from data ingestion, feature engineering, and model training through validation, deployment, monitoring, and eventual decommissioning. Unlike traditional software, models are probabilistic artifacts that drift, require retraining, and depend on complex data pipelines and hardware resources. MLOps therefore focuses on reproducibility, artifact provenance, and repeatable pipelines so teams can move from experimental notebooks to production-grade services with confidence. For learners, it helps to think of MLOps as the control room that converts research experiments into dependable services. It defines how models are versioned, how experiments are tracked, and how performance and safety gates are codified so that a model's behavior is both understandable and governable across its lifetime. Security in MLOps extends beyond code hardening to safeguarding the integrity of the entire pipeline, protecting datasets from poisoning, ensuring model artifacts are untampered, controlling who can publish to serving environments, and monitoring deployed models for anomalous behavior. The stakes are high because a compromised pipeline can introduce subtle but catastrophic changes, a poisoned dataset that shifts recommendations, a tampered model that leaks sensitive inputs, or a misconfigured deployment that exposes privileged connectors. Effective MLOps security embeds controls at every stage: secure data handling during collection, authenticated training runs, cryptographic signing of artifacts, and gated deployments through CI/CD pipelines that require explicit policy approvals. Teaching this means emphasizing both technical controls and governance. Developers must understand how engineering choices, permissive publish rights, lax staging isolation, or unchecked retraining become security risks when scaled. Model registries are the linchpins of safe MLOps because they store, index, and provide provenance for model artifacts and their metadata. A protected registry provides signed artifacts, tamper-evident metadata, and strict version control, so every deployment can be traced back to a specific training run, dataset snapshot, and set of hyperparameters. Provenance documentation answers critical questions during incident response. What data fed this model? Who initiated the training? Which evaluation runs passed? And which policies were in force? Restricting publishing rights reduces the blast radius. Only authorized build and release processes should be able to promote a model from staging to production, and registry APIs should enforce role-based checks and multi-person approvals for high-risk models. For learners, treat model registries as the safe deposit box of your MLOps practice. Artifacts live there with a ledger that supports auditability, rollback, and accountable governance. CI/CD for AI models reimagines continuous integration and delivery for artifacts that are large, stochastic, and data-dependent. Automated builds and deployments must incorporate not only unit tests but model-specific validations, performance baselines, regression checks on key slices, adversarial robustness tests, and policy enforcement gates that ensure outputs meet compliance requirements. Vulnerability scanning of container images, dependency isolation to avoid transitive supply chain compromise, and deterministic build manifests are essential because an innocuous library update or a compromised base image can propagate into production models. Rollback mechanisms must be rapid and validated. A failed deployment should revert to a known good model and configuration without orphaning stateful connectors or leaking credentials. In educational terms, CI/CD for models is not just automation for speed. It is a safety harness that enforces reproducible quality and policy adherence before models touch users or critical systems. Serving infrastructure is the outward face of MLOps, API endpoints, containerized deployments, microservices, or serverless functions that expose model capabilities to clients and systems. Each serving pattern brings trade-offs. Containerized microservices give control over resource isolation and network policies, but require orchestration and patching. Serverless endpoints simplify scaling, but can obscure resource usage and complicate tracing. Serving environments must be designed for least privilege, with minimal debugging interfaces exposed, clear authentication layers, and hardened runtime policies that prevent arbitrary code execution or unbounded resource consumption. Consider the edge case of a misconfigured debug endpoint. What begins as a benign internal tool can become a public attack vector that exposes model internals or data artifacts. As you teach serving architecture, emphasize that deployment topology is a security decision. Hosting, networking, and operational practices determine how resilient the model remains once it leaves the registry. Serving risks are a direct consequence of the interaction between exposed endpoints and imperfect models. Misconfigured endpoints, exposed debug interfaces, weak authentication, and denial of service vectors all create entry points for attackers. Misconfigurations can appear subtle: an API that accepts unchecked file uploads, an admin console accessible over public networks, or overly permissive CORS rules, and any of these can lead to data exfiltration or unauthorized model invocation. Weak authentication allows credential replay or token theft, enabling attackers to run costly extraction campaigns or to chain connector calls that cause real-world effects. Denial of service targets are particularly insidious in MLOps because models consume specialized hardware. Saturating GPUs with crafted requests can both cost money and degrade availability for paying customers. Teaching about serving risks means training engineers to think like defenders. Assume endpoints will be probed and design with the expectation that the most likely failures are operational mistakes, not exotic 0 days. Access control in serving is the practical enforcement point where identity, privilege, and intent meet the live model. Enforce strong authentication for every client mutual TLS, OAuth tokens bound to workload identities, or federated SSO for human users, so that every call carries a verifiable principal rather than an anonymous string. Per-model authorization policies map those principles to allowed actions: query-only, retrieval-enabled, plugin invocation, or administrative operations like model push and rollback. In multi-tenant systems, enforce separation at the token and namespace level, so one tenant's token cannot access another's storage, indices, or connectors. Use tenant-scoped encryption keys to reduce blast radius when keys leak. Monitor privileged accounts, closely rotate credentials, require just-in-time elevation for critical operations, and log every administrative action with attestation. Design authorization as policy as code, so rules are versioned, testable, and deployed through CI. That way, permissions evolve deliberately rather than by ad hoc exception, and governance can audit who was allowed to do what and why. Observability in serving turns ephemeral inference into a reconstructible narrative that supports debugging, detection, and compliance. Log request and response artifacts with correlation IDs that tie together retrieval contexts, model version IDs, system messages, and post-processing validators so a single trace reconstructs the full invocation path. Capture latency percentiles, error categories, retry counts, and resource utilization alongside semantic signals such as top K retrieval matches, grounding evidence, and validation results. These correlated metrics let you separate upstream data issues from model regressions. Integrate anomaly detection pipelines that surface sudden deviation in response entropy, spike patterns in policy rejections, or increases in unsupported claim rates. Balance retention and privacy. Redact or hash-sensitive inputs while preserving enough context for forensic replay, and ensure telemetry stores are access-controlled and encrypted. Observability is not optional instrumentation. It's the evidence you use to answer what happened, who triggered it, and how quickly did controls respond when incidents occur. Scalability and security present a continual set of trade-offs that define how you design serving topologies. Higher isolation per tenant clusters, dedicated GPUs, or separate index shards reduces risk dramatically but raises fixed cost and operational overhead. Conversely, shared pools are economical and easier to scale but amplify noisy neighbor effects and cross-tenant impact. Performance choices, edge caching, model quantization, or approximate retrieval often accelerate responses but change attack surfaces and recovery behaviors. For example, aggressive caching can obscure when a model or index update fixes a vulnerability. Ease of deployment through serverless or managed platforms speeds time to market but can hide critical telemetry and complicate rollback. The practical path is hybrid. Isolate high-risk tenants and critical endpoints while allowing shared low-risk flows to multiplex resources. Instrument everything and use budget-aware autoscaling to contain blast radius. Treat trade-offs as explicit policy decisions, not accidental engineering outcomes, and measure the business impact of isolation versus the savings from shared infrastructure. Model rollback and recovery are the safety valves that make serving survivable when mistakes or compromises occur. Maintain signed checkpoints and cryptographic provenance for every model artifact so you can verify integrity before promoting an artifact to production. Tie signatures to build systems so only authorized pipelines produce deployable artifacts. Implement automated rollback mechanisms that revert traffic to the last known good model version upon detection of policy violations, spikes in unsupported outputs, or integrity alerts, and validate that rollbacks can happen without leaving dangling sessions or corrupting stateful connectors. Test recovery procedures regularly. Run rehearsals that simulate a compromised deployment, measure time to roll back, and verify downstream services resume normal function. Preserve immutable evidence request traces, the offending responses, and the exact deployed artifact, so forensic reconstruction and regulatory reporting are possible. Recovery is more than code. It's practiced choreography that restores service while preserving confidence and legal defensibility. Zero trust principles applied to serving mean assuming every call is potentially hostile and designing verification into each interaction rather than relying on network perimeter protections. Employ strong identity at endpoints mutual TLS for service-to-service, short-lived signed tokens for client calls, and attested workload identities for server-side agents, so you can authenticate and authorize at each hop. Segment networks and enforce minimal reachable surfaces for model endpoints. Isolate management planes from inference planes and require explicit authorization to bridge them. Implement continuous validation. Reevaluate risk during sessions, require step-up authentication for sensitive actions, and revoke tokens automatically on anomalous behaviors. Use policy as code to express fine-grained constraints, who may invoke connectors, which retrieval indexes are allowed, and which output formats can trigger actions, and enforce them at runtime. Zero trust does not mean zero usability. It means instrumented, auditable assurance that each call is checked, logged, and bounded in its potential impact. Monitoring for abuse at the serving layer focuses on signals that show misuse in progress and enable fast containment. Watch for abnormal inference traffic patterns, high-frequency queries, sudden increases in long context or maximum token requests, and repeated variants of prompts that probe validation boundaries, which often precede extraction or resource abuse campaigns. Detect prompt injection attempts by tracking sequences that include known injection markers, repeated attempts to bypass validators, or fast iterative probes that adjust phrasing to evade filters. Resource spike anomalies, GPU hours per key, sudden surge in concurrent sessions for a single token, or repeated large batch inferences should trigger throttles and investigative alerts. Integrate these detectors with your society so alerts include rich context model version, retrieval snapshot, sample inputs, and recent policy rejections, and automate containment steps such as temporary token revocation, reduced model fidelity, or rerouting to human-in-the-loop handlers. Monitoring becomes meaningful when it's tied to action. Detect early, contain fast, and restore service with minimal collateral impact. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Defensive gateways act as the first and most deliberate line of defense for serving infrastructure, functioning as an API firewall that inspects, classifies, and enforces policy on every incoming request before it touches model runtime. Think of a gateway as a gatekeeper that performs syntactic validation, schema enforcement, payload inspection, and lightweight threat scoring at network speed. It drops obviously malformed or oversized requests, enforces quotas, and tags traffic with risk metadata for downstream services. Gateways matter because they reduce the attack surface exposed to expensive model inference. By catching long context padding, embedded injection markers, or malformed binary blobs at the edge, they prevent costly decoding and reduce the need for expensive downstream mitigations. Implement gateways with layered decisions fast allow/deny filters, rate limiters that consider identity and tenant, and enrichment hooks that append identity, device, and session signals, so that more expensive checks can focus only on plausible threats. Operationally, place gateways close to ingress points, instrument them heavily for telemetry, and treat gateway policies as versioned auditable artifacts that are part of your CI/CD and governance flows rather than ad hoc knobs tuned in production. Infrastructure as code hardening brings security into the provisioning layer by codifying safe configurations, preventing drift, and enabling automated compliance checks before resources are created. Define secure templates for networks, compute tiers, storage buckets, and role bindings, so every environment is instantiated from an approved blueprint that enforces least privilege and segmentation by default. Integrate automated policy as code engines, such as policy linters or cloud-native policy enforcers, into CI, so any IAC change is validated against governance rules, no public S3 buckets, VPC defaults enforced, or compute roles constrained to required APIs only. Version your IAC pipelines and require peer review for changes to security-sensitive modules, ensuring that Terraform plans or CloudFormation diffs are reviewed and signed before apply. Include drift detection and periodic reconciliation jobs that report deviations from approved topology, triggering remediation or automated rollback where appropriate. Treat IAC as the locus of truth for your infrastructure posture. When you change policy, update templates, test in staging, and let automation propagate safe defaults reliably across environments. Secrets management in serving is the runtime technique that prevents hard-coded credentials, leaked API keys, and sticky tokens from becoming the weakest link in a live model deployment. Integrate a centralized vault that stores credentials encrypted at rest, issues short-lived tokens on demand, and injects secrets into containers or serverless instances at startup or invocation time, rather than baking them into images. Automatic runtime injection reduces human error. Services request ephemeral credentials scoped to the minimum privileges and lifetime required, and the vault records a detailed audit trail of every issuance and revocation. Enforce rotation policies, automatic revocation on suspicious access patterns, and hardware-backed key protection for the most sensitive material. Additionally, design for defense in depth by combining vault-provided secrets with MTLS between services and role-bound access policies. So even a leaked token is constrained by network segmentation and rapid expiration. Finally, log and monitor secret access patterns, unusual issuance rates, cross-tenant requests, or out-of-hours fetches as high-priority alerts tied into your society playbooks. Because credential abuse is often the first step in escalatory attacks, model monitoring tools form the practical observability layer that detects drift, adversarial inputs, and validation failures in serving pipelines, and choosing the right set of monitors is a strategic decision. Drift detection systems track statistical shifts in input distributions, feature embeddings, and output entropies, raising alerts when inputs or outputs depart significantly from training baselines, early warning that model behavior may degrade or that a new user population is being exposed to the model. Adversarial input alerts look for sequences typical of prompt injection, repeated paraphrase attempts, or rapid iteration patterns, often using ensembles of lightweight classifiers and behavior heuristics. Output validation modules implement the checks described earlier: syntactic enforcement, semantic grounding, and toxicity detection at scale, and produce structured verdicts that can be acted upon automatically or routed to human reviewers. Integrate these tools into dashboards with per-tenant slicing, historical baselining, and drill-down tracing so incidents are reproducible and remediation is measurable. Importantly, keep monitoring tools modular and pluggable so you can evolve detectors as adversaries do without re-architecting the entire serving stack. Policy enforcement in serving operationalizes business, legal, and safety constraints so models adhere to acceptable use rules continuously rather than relying on periodic manual audits. Translate high-level policies. No disallowed medical advice, redact personal data, or require citation for regulated claims into executable rules embedded in the serving pipeline, validators that block or redact outputs, gating checks that require human approval for certain actions, and runtime policy evaluators that refuse connector invocations unless caller context meets compliance criteria. For regulatory compliance, make enforcement auditable by logging policy evaluations, storing evidence packets of blocked responses, and versioning rules so you can show how a decision maps to codified policy. Implement continuous enforcement by tying policy deployment into CI, so rule updates are tested against representative suites and canaries before rollout. Governance teams should own the policy taxonomy while engineering owns the enforcement code. This split ensures that legal intent becomes reliable machine action with testable boundaries and clear remediation pathways. Strategic relevance of MLOps in serving security extends far beyond technical hygiene. It is a business enabler that determines whether your AI investments can be trusted, scaled, and monetized. Secure MLOps lowers operational risk by preventing catastrophic pipeline compromises, poisoned data, tampered artifacts, or exposed connectors that would otherwise translate into regulatory fines, customer churn, and lost contracts. It also shortens procurement cycles. Enterprise buyers look for auditable registries, signed artifacts, and CI/CD gates as evidence that a model will behave predictably in production. Security in serving is therefore not a cost center only. It is a differentiator that permits higher assurance offerings, premium SLAs, and partnerships requiring stringent controls. For the engineering team, strategic alignment means prioritizing investments that reduce mean time to detect and remediate, enable safe feature velocity, and preserve trust, so you should evaluate controls by their ability to reduce business-impacting risk, not merely by technical elegance. Begin an implementation roadmap by focusing on the highest leverage controls you can operationalize quickly. Inventory your surface first. Enumerate models, data sources, connectors, and the identities that can publish or serve artifacts. Next, establish a hardened model registry and require cryptographic signing for any artifact promoted to staging or production. Pair this with CI/CD policies that gate deployments on passing evaluation suites, security scans, and policy checks. Implement secrets management and vault integration before broad rollout, so tokens never live in images or code. Stand up defensive gateways and per-key quotas at the edge to throttle abuse and prevent careless resource waste. Finally, attach monitoring and observability to each stage train. Validate, serve so telemetry drives fast detection and rollback. Triage these steps into quarter-sized milestones. Validate with red team and evaluation runs, and expand coverage iteratively, rather than attempting a monolithic, secure everything migration. Organizational practices determine whether technical controls stick, so embed security into roles, responsibilities, and release norms rather than treating it as an afterthought. Create cross-functional ownership. Designate an MLOps engineering lead to own build and deploy plumbing, a security champion to own policies and audits, and product owners to sign off on risk acceptance. Use policy as code so authorization and content constraints are versioned, reviewed, and testable, just like software. Enforce them through CI gates and automated validators. Establish SLAs for detection and remediation, mean time to detect, contain, and rollback, and tie those into on-call rotations and escalation paths. Train teams on incident playbooks and run periodic drills that simulate compromised registries or runaway inference costs. These cultural investments pay dividends. When everyone knows the playbook, remediation is faster, and secure patterns become the default development path rather than an optional add-on. Continuous improvement is central to MLOps security because models, data, and adversaries all evolve. Make testing, telemetry, and post-incident learning the operational rhythm of your program. Automate evaluation pipelines that run regression, robustness, and policy tests on every candidate checkpoint. Feed failing cases into training and validator updates so the system hardens over time. Use red team campaigns to surface novel bypasses and incorporate those artifacts into both the eval suite and detection signals. Measure detector efficacy, false positive cost, and time to remediate so tuning balances operational burden with exposure reduction. After each incident, produce a structured postmortem that maps causal factors, artifact provenance gaps, missing telemetry, misconfigured gateways to concrete remediation tasks, and CI checks that prevent recurrence. In this way, your MLOps lifecycle becomes a feedback loop. Models are not only deployed and monitored, but actively improved by adversarial pressure and production lessons. To conclude, securing MLOps and serving is a multidisciplinary program that combines artifact integrity, CI/CD rigor, runtime hardening, observability, and governance into a cohesive capability that enables safe scaling of AI products. The practical actions you can start today are clear: inventory and provenance, gated CI/CD with policy as code, vault-back secrets, defensive gateways, container and IAC hardening, and layered monitoring tied to SOC playbooks. Equally important are organizational behaviors, cross-functional ownership, incident rehearsals, and measurable SLAs that make those technical controls effective in practice. This security posture aligns with zero trust principles and prepares you for the wider supply chain hardening that follows. The next episode will examine supply chain security in detail so you can extend these protections to third-party models, datasets, and tooling with confidence. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.